So, hello, and I welcome you all in this second lecture of natural convection. So, first of all, in the start, I offered you my apology because of a very bad mistake that I committed in the previous lecture. And what was that? That was this thing. Okay. Speed of sound is not this, that is dpdv, but it is wrong. So, it is actually dp rho. Okay, and that is why i I am someone who hates to memorize things. Okay, I'm someone who hates to memorize things because I have tried a lot, but I have seen that the moment I try to memorize anything, okay, it go, it goes wrong. So just because I did this mistake, okay, I will have the punishment and I will derive this thing. This is not very hard. Okay, and in any of my lectures, whenever I try to memorize anything or whenever I try to write by memorizing anything, then I always recheck it after the lecture because there is a fair chance that I have mistaken about the thing. Okay, so first of all, that means we have done the right things up till here, where uh, dpd rho, right? So up till here it was right, up till this part. So let me just delete this part. Okay, and see all these things. I say that I am just like you. Okay, I am actually not teaching you but sharing with you whatever I have learned. So if you find that anything is, I mean, anything seems wrong or seems illogical, then you always have the right to comment that in the comment box. There is no issues of ego. Okay, because I never think that I know everything, or in the other way, I always think that I almost know nothing, or I know as much as you can know. Okay, so here we are learning together, not the thing that I am just uh, teaching you something. So if it was a physical lecture room or physical classroom, it could have a nice discussion between us. Okay, so I want that discussion in the comment box. Okay, so now let me just prove it. What that is, dp rho is equal to c square. Okay, so obviously for no losses and, I mean, reversible processes, so and insulated ones. So this is for constant entropy, that is the reversible adiabatic processes. Clear? So, or for the time being, let me just, I mean, remove it. Okay. So what we will do is, let us say that there is a disturbance. So what kind of disturbance? If you have studied the compressible flows, we take these as pressure disturbances, specifically as you can consider it as your sound. Okay, the sound that right now you are getting from my mouth. Okay, so this is a pressure wave or pressure disturbance. Okay, traveling with a speed c. Okay, and this is with respect to the medium. Clear? So it is traveling with a speed c. That is fine. Now if I draw a coordinate axis like this, so it is moving along the positive x direction. That is fine. So So to avoid the ambiguity that this pink or this violet line is not the y-axis, what I will do is, let me just extend this. And this is the positive x-axis, and this violet line is not the positive y-axis. It is denoting the pressure disturbance, right? And here we have the fluid. If you think that you already know this, you can skip this part, okay, and you can go to the next part of the lecture. Clear? Okay. So now this is the fluid. So here this is a disturbance. So the fluid properties in this side and the fluid properties at this side, they will be different. Okay. So now we will analyze it with the we will analyze it with a situation that this is at rest, that is the disturbance wave at rest. Okay, fluid is moving in negative x direction with minus c velocity. Okay, so if I again draw it, or I can just copy paste it. Okay, so now I will just change the color of the velocity. Now this is the fluid. Okay, sorry about that, just the mail had come. Okay, so now this is the fluid. Okay, now because this is a disturbance, okay, in this side I will consider that at this side I have the velocity of the fluid as c, and at this side I have the velocity as c minus dc. You can also write c plus dc. I am considering that at this side the velocity will reduce. Okay, and after this rho, so rho minus d rho. Okay, then maybe t, so t we will not actually require, and what else we will require? Okay, maybe this is enough. Okay, okay, so p, pressure we will require, so p minus dp. Clear? So if that is the case, now we will take a control volume like this. Clear? And I will just make it dotted because generally in fluid mechanics we show the control volumes by dotted lines. Okay, so this is my control volume that is encapsulating the disturbance wave. Okay, now we have to write the mass balance and momentum balance across the CV. Okay, so firstly the mass balance. Clear? So the mass balance will give rho, okay, into A into C. A is what? So A is the area of this control volume. Okay, I should write the cross sectional area. Okay, or the frontal area. If you can look from this side, you will see the area like this. This area is A. Clear? So rho SC, that will be equal to rho minus d rho, clear, into C minus dC. A will be A, right? Now if we just write it, if we just break it down, so rho C A, right, minus rho A dC minus C d rho A plus d rho dC A. Okay, now considering that this d rho and dC are very small, this would be even smaller, and thusly I can neglect it. Okay, so this will be what? That means from this equation we can write minus C d rho is equal to rho dc. Clear? So if I can give it a name like equation 1, okay, then I will write the momentum balance. Okay, so if we write the momentum balance, then see the force that is acting is due to the pressure, right? So P into A, okay, minus P minus dP into A, okay, so this is the force due to pressure, or it is a surface force, and this will be equal to the change in momentum, okay, or the momentum that is in, I mean going in minus momentum that is going out. Okay, so what is the momentum going in? That is rho c, okay, rho c square into A, right, because rho ca into C, and minus rho minus d rho into C minus dc, okay, square into A. Okay, so now what we can do is, by simplifying this equation, we will see that dP into A, so A actually we can cancel out. So in this equation we will have only dP, and here we will have, let us see, okay, so what we can do is we can write it as minus rho minus d rho. Now, okay, so rho minus d rho into C minus dC, okay, or let me just break it down. So C square, okay, minus 2C dC, okay, and plus dC square into A. So obviously we will just neglect it. Okay, now what else is there? Rho C square into A minus rho dP. Now 2C dC is as good as dC square, okay, into A, right? So again rho C square into A minus rho C square into A minus rho d of C square, right? Okay, so minus, okay, so plus plus okay, so here I have to multiply A plus A C square d rho, sorry, this will be also minus, right, and this will be 2C dC into d rho into A. This part I have multiplied this with this, right, and obviously this we will neglect, right, this will be neglected. So what will be this? This will be A, okay, so A will be cancelled out actually, or let me keep the A here. Okay, so this will be A rho, or let me write it like this, 2C dC into A rho, right, plus A C square d rho. Clear? So if I have done the right things, so let me see, there is some additional term coming here, right? Maybe I have committed some mistake. Okay, maybe I have committed some mistake. Okay, let me do it in another way. Okay, I'm sorry for these things. Actually, I should come, I mean, prepared. That is the thing, but honestly, I can't find for the time for extra study. Okay, so let me do it once again. So dp into A. Okay, that is rho c square to A minus now rho minus d rho into C minus dc, that is as good as rho into C. Okay, so rho into C minus dc into A. So from this equation I have write rho minus d rho into C minus dc as rho into C from the mass conservation. So this is equal to rho c square A and minus rho c square A plus rho C dc into A. Now this is, I mean, looking handsome, right? So dp is equal to rho C dc. Clear? Now you see that here we have actually told that my rho into dc is equal to C minus C into d rho. Okay, is equal to minus C into d rho. So rho into dc is equal to minus C into d rho. So it will be, so this is what, C into rho dc, and this will be C into minus C into d rho. Okay, and here we have made a mistake. Okay, that is there should be plus and minus. Okay, this actually you can correlate if you just if you just look at the direction of the pressure. Okay, so actually this is the positive direction that we have chosen. This is the positive direction. So that is why that should be P minus dp into A minus P into A. Okay, this is the positive direction. That is why the positive force should be in this direction, and that is equal to the momentum in minus momentum out. Clear? So that is why this should be the minus. Okay. So this will be minus P minus dp. Okay, and now this will be dp d rho is equal to C square. Okay, so we have proved this. So one thing is there, that here no energy input is happening, so it is adiabatic, you can consider. Okay, but currently we are not taking it as isentropic. Okay, but it can be shown that it is reversible actually. Okay, that is the that this process is reversible. Okay, that is we get the speed of the sound when we write del p del rho s. Okay, so we can actually show that the change in entropy, okay, of both the surroundings and universe is very small during propagation of sound waves. Okay, this can be shown in compressible fluids. Okay, in compressible fluid mechanics when you study it. So we get this thing. So this is proved. Now let us move on. Okay, so here I will just copy it. Okay, so I will just copy it here. Okay, so let us cast this thing. Okay, I will start from this in terms of the rho. So this will be 1 by, okay, so rho r, that is density at reference state, minus rho r. Okay, so it will be minus 1 by rho r square into d rho dp at constant entropy at Tr comma Pr. Okay, so this will be gamma by rho r dp del rho del ps at constant entropy at Tr comma Pr. Okay, now we know that this is your C square. So del p del rho was C square, so del rho del p will be 1 by C square, right? So Why it's not working? Okay. So we got our Kr superscript T, that is the isothermal compressibility, as this one. Okay. So now if you have followed my previous lecture, okay, so then we can write rho as this, and if I neglect the higher order terms, okay, so then how can I write this equation? So let me just copy it. Array, sometimes it does not work. Why, I don't know. Okay, so I will paste it and I will make it smaller. Okay. So here, if I continue with this, this will be rho is equal to rho r into 1 plus, so let us see what is this. This we have derived as your minus beta r, right? So minus beta r, this is into delta t. Okay, and what is the second term? The second term is, okay, kt into r, right? Sorry, kt is subscript r. So let us see the second term. The second term is this, and that is equal to k superscript t subscript r. Okay, and that we can write as, I have just shown, gamma into this part, that is gamma by, okay, so gamma by rho r c square into delta p. Right? So now what we can do is, see, okay, so here we have this equation and this is a linear approximation. Okay, now if I tell you, I gave you a homework, although I hope that many of you have not continued up to that part. So the thing is, just let me check that if I have done it correctly or not. Gamma into kr, and I think that is fine. Okay, that is fine. Okay, so now let us consider in, now let us focus in this number. Okay, this parameter. Okay, so let me once again just check. Fine. So you see that rho r for ideal gas, we can write it as PR by RT by C square, right? That is true. Now this is what gamma RT, that is actually the speed, okay, of, okay, the speed of sound at that medium, okay, the speed of sound or speed of a I mean pressure disturbance at that medium, and this we can write at a square by c square PR. Okay, so if I write this equation again, So again, if you have not studied the compressible flows, then it can be a bit tough. Okay, but this thing is actually we write as a square, where a is the speed of sound at that medium, okay, having temperature T, okay, and gamma is the property of that medium, okay, and c is actually the sonic speed, okay. So now rho is equal to rho r into 1 minus beta r delta T, and this a square by c square, okay, this is actually the Mach number, okay. Now this is we write as Mach number, m, or write m, let me write m only, Mach number square. It is not actually Mach, the pronunciation is Mach, okay. So this is PR, clear, P reference, this thing. That means for low speed flows or for low Mach number flows, okay, so for low Mach number, so I also often call it Mach number, okay, due to my bad habit, but it is called Mach number, not Mach number. So for low Mach number, we can write, or we can write actually rho is equal to rho r into 1 minus beta r into delta t r I should say, okay. So generally we can take this delta t r, so actually this delta t r means delta t, okay, okay, so I can directly just write it, okay, because the reference state is nothing but T infinity, okay. So okay, yes, or I should directly write that because we take the reference state as infinity, we will write rho is equal to this. So this is our linear approximation for rho, and this is very important, okay, that for low Mach number it is valid, okay, otherwise you have to consider the change due to the change in pressure also. This is very important, okay. So we have found an expression for rho in terms of temperature variation, okay. So now let me write the governing equations. I have already, I think, described the physical problem, right? That is the flow. Have I described? Yes, okay. So for this problem, that is natural convection for a vertical flat plate, isothermal flat plate. So let me just copy this picture, copy this diagram, okay. So I have copied it, okay. So now let me write the governing equations. So the governing equations, okay. So here the momentum equation will be a bit different, and can you just directly point it out that what is the basic difference between the momentum equation, or I should say that what is the basic difference between the treatment in momentum equation if I compare this natural convection with forced convection? The basic difference is that in forced convection this rho u, okay, and T, okay, so T was coupled with u, but this rho was not coupled with u because this rho was not a function, sorry, this rho was not coupled with T, okay, but now this rho is coupled with T, okay. So I have to know the solution for rho, then I can solve the momentum equation. So in the forced convection we considered that rho is a constant, and that made our life easier. But now rho is a function of t, so we cannot say that rho is a constant and we solve the momentum equation. No, we cannot say that. Ideally, now the momentum, ideally we can say that for the forced convection we had a one-way coupling. Okay, one-way coupling. That is, we can solve the u, that is the velocity, from the momentum equation independently. After that, using that u, we can solve the energy equation. But now we have a two-way coupling. Because rho is a function of t, we can say that we have to first solve the energy equation, then we can, or we don't have to first solve the energy equation. Both the energy and the momentum equation have to be solved simultaneously, because now finding u, after finding u only you can find the variation of temperature, because the energy equation is having u, and after finding t only you can find the u, the velocity, because in the momentum equation the rho is dependent on t. So now this is a two-way coupling. Okay, now this is a two-way coupling. So this is the basic difference between the governing equations of forced convection that you might have studied and the natural convection that currently we are studying. So in the forced convection also, if we have very high Mach number fluids, then the rho can change with pressure, and otherwise if the isothermal compressibility, okay, is not very low, okay, or I should say the isentropic compressibility also, if it is not very low, then also the density can change with temperature for forced convection. Then you have to consider that into your mathematics. Okay, so now I don't have that much charge in my iPad. I will only go up to 1%, then I will switch it off. Okay, so let me see how much I can cover. So the governing equations, firstly I will write the momentum equation and I will write the x momentum. Okay, so the x momentum, let me write it with different colors. So x momentum, clear? So the x momentum looks like this for steady flow, obviously. So rho u into du dx, okay, v into du dy is equal to minus dp dx plus mu into this ones. Clear? Okay, and I have missed one thing, that is minus rho g. Clear? That is the body force. This is the x momentum, right? And let me write again the continuity. So for an incompressible 2D flow, continuity reads as del u del s del v del y is equal to 0. Okay, so now the thing is, there is a very interesting fact. Okay, firstly I will show you that we can apply the boundary layer assumptions here, but unlike the forced convection, here the concept of the hydrodynamic boundary layer and the thermal boundary layer are not very much different from one another. Here you don't have a clear and crisp difference in hydrodynamic and thermal boundary layer. Why? Because here the variation of temperature will dictate the velocity. Have you understood that in forced convection the velocity was provided externally by the external pump, by the external pressure gradient, but now the temperature difference, that is, if I talk about the reference temperature difference, that is T infinity minus Ts, this temperature difference is guiding the velocity. So at a distance, so if I consider that this is the layer, I can make it dotted also. Okay, this is the layer up to which there is a significant temperature difference. So after this layer ends at this region, because the temperature difference ends, you can say that the velocity of the fluid will also be very low. Okay, will also be very low. Clear? Okay. So now that means we will call this as something like a heated layer. Okay. So I will write it as delta. So delta is, okay, thickness of the heated layer, I would say. Thickness of heated layer. But there are some special fluids depending on the, Prandtl number, okay, because of which if the moment of diffusivity is very large, understand these things, if the nu is very large compared to alpha, it can be the case that the heated layer, above which the temperature difference is almost negligible, okay, that has ended up to this point, but because the nu is very high, we have the x component of velocity there up to this layer. Okay, this can be the case, and obviously if I draw the velocity profile, this would be something like this. Okay, ideally. I am not saying that the maximum is at the middle point of the delta, that is at delta by 2. It can be anywhere, we will see later, but before that I am saying that it will be something like this because this fluid is at hydrostatic state. Clear? So this is the boundary layer thickness, the heated layer thickness. Now considering this simpler case where we are only considering this heated layer and we are not considering the difference between the velocity the velocity boundary layer and the temperature boundary layer, we say that for delta by L much less than 1, okay, boundary layer assumptions are valid. That is, this heated layer will behave like a boundary layer. Now here, if you have studied boundary layer carefully, we can apply this assumption only for large RE flows, large Reynolds number flows. Now here, what is that number depending on which we can apply this assumption? I will show you that, okay, and that number is actually called the Grashof number, and how that comes I will show you. Okay, so here now if I have the boundary layer assumptions valid, that means now my governing equations will be the x momentum. Okay, so if this is valid, so now I will write the x momentum again. So the x momentum, clear, the x momentum would be what? Rho into u du dx plus v du dy is equal to minus dp infinity dx, right, plus mu into, only this term will be there, minus rho g. Clear? Then the y momentum. So the y momentum would be, okay, clearly del p del y is equal to 0 directly from the boundary layer equations. Okay, there is a playlist for the whole convection heat transfer in which I have in detail explained the boundary layer theory. Okay, so if you don't know the boundary layer, then you can go to that, and I have already mentioned that this is nothing but a continuation of that series. So I can expect that you know these things already, because if you are studying convection, no one starts convection from studying natural convection. Okay, so finally I will have the continuity. Okay, so the actually the continuity will be same. Okay, there will be no difference. So now it is 2% charge. I will only wait till 1% charge. Okay, otherwise this recording will gone. Okay, if the tab switches off by itself. Okay, so now these are my bound equations for natural convection for obviously the velocity after applying the boundary layer assumptions. Now we will work with this x momentum equation. Okay, let me write first the temperature also. Okay, so the energy equation, let me complete it. Okay, after applying the boundary layer assumptions, okay, the energy equation will be rho u del t del x plus v del t del y, obviously under the bracket, and that is equal to, okay, alpha this into this. Clear? This will be the equation. Okay, I think I have not missed anything. Okay, plus the source term, but the source term is not there. Okay, so let me stop this lecture here, because we have already a very less amount of charge in my tab. Okay, but next we will apply something called the Boussinesq approximation. Okay, and we will see that how it can change the x momentum equation, and that will be the sole equation, that will be the main equation for the natural convection. Okay, and I again apologize for the mistake that I have committed in the previous lecture. Okay, and I cannot ensure that I will not make those kind of mistakes again, but I will try not to make those mistakes. Okay, actually my schedule is becoming more and more hectic nowadays, because of which I am not getting any extra time to study all these things. Okay, so I will try not to make those kind of mistakes. So we will meet in the next lecture, where I will start with the Boussinesq approximation. Until that, goodbye, take care, and thank you.